In a previous video, we looked at the slab waveguides, and we said if you use Maxwell's equations and you calculate the solutions numerically, and then you create a diagram, you end up at something like this. So if you plot then in a diagram the omega value versus, excuse me, the k value, then you get different types of solutions. You get some sort of discrete lines over here, and then you also get a continuum of solutions over there. And what we're going to do in this video is focus on this discrete part, these discrete solutions. And I will be assuming that you've seen waveguide theory before, so this will mainly be a short refresher or perhaps a slightly different perspective on things. So let's return our attention to this, this diagram over here. And because you have these so-called bands here, these lines are called bands. This also means that this diagram is sometimes called a band diagram. Now again, as I already said, every point here in this diagram corresponds to a certain solution to Maxwell's equations, so to a mode if you want. But people typically use the term mode not to refer to a single point on this line, for example, but to the entire family of solutions that you have on a single line. If you solve Maxwell's equations numerically and you look at the field profiles corresponding to these guys, to these discrete lines, these discrete bands, then you will quickly see that these field profiles correspond to the guided modes of the structure. So for example, over here, you have the fundamental guided modes, where you have the field profile basically concentrated in the core. And then over there, you have higher order modes, so the first order modes, and successively more and more oscillations that you have in the core, but still light is contained mainly in the core. So this is why we're talking about guided modes. Now we can introduce this index n here to talk about the different types of guided modes that we have, with n equal to 0 corresponding to the fundamental mode. And that means that we can identify any guided mode in this diagram by using some sort of an extended label. First of all, a label k to tell you which point on the horizontal axis we are, and then another index n, which tells you which mode, which band that you're looking at. Unfortunately, n here is the same symbol as refractive index, but of course this is a different quantity, so don't confuse these two things. Right. Another thing which is worth pointing out in this diagram is that these guided modes, these guided bands, it turns out that they're basically contained in between two straight lines here. Why is that? Well, you also know from waveguide theory that if you have the effective index of your guided mode, this is basically contained between the refractive index of the core and the refractive index of the cladding. And if you have two different claddings, then here we mean the highest refractive index of the cladding. If you translate this condition here to a graphical condition that you can plot in the band diagram, you basically get the following. So let's have a look at the solutions that can exist in a uniform medium. So let's say, for example, a uniform core medium or a uniform cladding medium. What are the relationships between omega and k? Well, you know that in uniform medium, k is going to be equal to omega divided by the speed of the wave. And the speed of the wave is given by speed of light in vacuum divided by the refractive index of the material that you're looking at. So you get n omega divided by c. Now to plot this type of relationship in our omega versus k diagram, we need to write this as follows. Writing omega as a function of k, we get omega equal to c divided by n times k. So let's plot, for example, all the different solutions that you can have in uniform cladding material and in uniform core material. So since the core refractive index is the highest, this means that you divide by the largest number, and this means that you end up with the smallest omega values. So over here you have a line corresponding to kc divided by n core, and the line over there turns out to correspond to kc divided by n cladding. So just translating the condition that your effective refractive index of your modes lies in between these two values, if you translate that to an omega k relationship, this will give you these two lines over there. But obviously that line also called the light line, because this gives you the transition between these modes over here, the discrete modes, and the continuous modes over there, which we will talk about in the next video. Okay, with these things out of the way, let's try and answer a final question. Why is it actually that these guided modes form a discrete set rather than the continuous set that you find over here? So pause the video and see if you can find the physical reason that explains why you only have a discrete set of guided modes. So from waveguide theory, I guess you are familiar with this image of a guided mode. If this is the core over here, this guided mode basically consisting of a plane wave, which is bouncing up and down between the interfaces between the core and the cladding. So let me redraw this a little bit. So you have your core over here, and then you have a plane wave, which is bouncing up and down like this. Now, obviously, the angle that this plane wave makes with the horizontal, that will result in a different value for the propagation constant along the horizontal propagation direction, for example. So saying that you only have solutions for discrete values of k basically means saying that you only have solutions for very specific angles of this plane wave bouncing up and down in the core of the waveguide. Now the question becomes, why do you only have guided modes if your angle has very specific values for this plane wave bouncing up and down? Well, think back to what an eigenmode basically is. It's a field distribution that can propagate indefinitely without fundamentally changing the intensity of its shape. So you should have something that can propagate indefinitely without having a source that can help move it along. Now, the way this can happen, or the only way this can happen, I should say, is that if you look at your plane wave, which is merrily bouncing up and down in the core here, and you look at a full round trip of this up and down bouncing, and if you compare, for example, this point over here with an equivalent point over there, if you're in a situation that the phase at the point B is exactly the same phase at the point A, modulo 2 pi, of course, then that means you will have a resonance condition set up, and then the whole thing can repeat itself indefinitely, basically. So we will only be getting a self-sustained propagation thanks to a resonance condition if the round trip phase of the plane wave up and down here in the core, if that round trip phase accumulates an integer multiple of 2 pi. So this really explains why only for very specific angles you obey that resonance condition. Otherwise, you would get something that gets jumbled and which does not keep its shape upon propagation. So this explains why you have a discrete set of guided modes. And then finally, just to be complete here, obviously you will need to have total internal reflection such that all of the light here gets reflected at the interfaces. But still, there will be a part of the light that will evanescently leak out of the core, and this will give rise to these evanescent tails in the cladding. But again, this exponential decay does not correspond to propagation in that direction. It's just some leakage of light, which is mainly contained in the core and travels in that direction over here.